Hello everybody. I, Professor Patil, welcomes you to the world of digital signal. In today's lecture, we will learn the sampling theorem and the perfect sampling frequency using which the signal is sampled and recovered back to the original signal. So let us start with the sampling theorem first of all. Before going to sampling theorem, we should know that why there is a need of sampling theorem. Or any discrete time continuous signal, it may be represented as an analog signal as well, cannot be processed by the digital computers. Now let us consider an equation with x of t is equal to a cos omega 0 t plus theta. In this equation, the t represents the continuous time signal. F, that means omega 0 is equal to 2 pi f, and that f represents the frequency in hertz. Here x of t is a pure cosine signal given by this formula. Now this signal is a continuous signal. It moves continuously in the time domain up to the infinite time, and hence the digital computers cannot process this signal because digital computers operate only the discrete time signal or the discrete time versions of analog signal, and that signal can be represented as x of n is equal to x n ts. Here n is the sampled version of original signal and ts is the sampling frequency using which that signal is continuously sampled. So this sampling frequency we need to know, using which the analog signal can be perfectly sampled. The process of converting an analog signal to the discrete time signal is called as a sampling, and that sampling converts x of t into x of n, which is performed by the analog to digital converter. This sampling process can be visualized as a simple switch which opens and closes at a fixed interval of time ts. So let us define the sampling theorem in the straightforward statement. The sampling theorem is stated as a continuous time signal can be represented in its samples and can be recovered back when sampling frequency fs is greater than or equal to twice of the highest frequency component of the message signal. So in mathematical form, it is represented as fs is greater than or equal to twice fm. Note, note that here the minimum sampling rate is twice of the f max. This is called as the Nyquist rate. Now Nyquist rate is represented as simply the fs is greater than twice f max. With the basic understanding, we shall now formally prove the sampling theorem. The sampling theorem was introduced in 1949 by the Claude Shannon, a research mathematical at the Bell Telephone Laboratories, and he was a faculty at MIT. The sampling theorem hence also sometimes called as the Shannon sampling theorem. In order to represent a continuous signal in the discrete domain without any loss of information, it is very much necessary to take as many samples of the original signals as possible. Higher the number of samples, better its representation. The Shannon theorem, that means the sampling theorem, tells us what should be the minimum samples required faithfully to represent a continuous time signal. So we will now prove this sampling. Consider the continuous time signal here is represented by the signal x of t. So this is our signal x of t, which is a function of time. This signal is get multiplied with a multiplier, and this multiplier is nothing but the impulse train delta t of period ts. So this x of t, a analog signal, and this impulse trend delta t are both get multiplied in this multiplier, and we will get this y of t. This y of t is called as a sampled signal. It is a discrete sampled signal. So it can be represented like y of t is equal to x of t into delta t. So let us derive the complete proof of sampling theorem. We, that sampled signal is indicated with the equation y of t is equal to x of t into delta t. Let us take the trigonometric values of delta t, and it is given by the equation delta t is equal to a0 plus the summation of n is equal to 1 to infinity of an cos n omega st plus bn sin n omega st. Here, the a0, an and bn are the three components which we are defining in terms of t. So a0 is given as 1 upon ts integration from minus t by 2 to plus t by 2 delta t of dt. Now we know that as it is a impulse response, it exists at t is equal to 0 only. So let us put t is equal to 0 here, and we will get it is 1 upon ts. Similarly, in the equation of an is equal to 2 upon ts integration from minus t by 2 to plus t by 2 delta t cos of n omega s dt. Here also this t will become 0 as it is an impulse response, and we get the complete, this term will be equal to 1, and hence the equation will become 2 upon t. And similarly for bn, as here it is a sine signal, and delta 0 and sine n omega 0. So sine 0 is equal to 0. So this all 0 term is get multiplied with this 2 by ts, and we get the answer 0. Now put this a0, an and bn, all these value in the equation number 2. That means this equation. So here a0 will be given as 1 upon ts. This is value of a0. Then an cos n omega st, its value is 2 by t. So here it is 2 by t. This is the value of an only, and this cos n omega ts will remain as it is. And here sine bn sin n omega sts, its value is 0. So this 0 value will be written here. So after simplification of this equation, we will get only two terms in that, 1 upon ts plus summation n is equal to 1 to infinity into bracket 2 upon ts and cos n omega st. Now this dt value, this value of dt, now we will substitute in this equation number 1 here dt. So we will get the next equation as y of t is equal to x of t into delta t. So here we are putting the substitution of delta t. So it becomes this one from the previous slide. So x of t is equal to 1 upon ts summation 2 upon ts cos n omega st. Now let us multiply this x of t to the both of this factor. We will get this first term and this second term. From both terms, 1 upon ts is taken outside as a common parameter, and now in the bracket we are left with this x of t as it is, and when we are expanding this summation, we will get this equation as it is. If we are taking the Fourier transform on the both side, then that time domain will be converted into frequency domain, and the time parameter is shifted as a omega parameter, that means the frequency parameter. So we will get the equation y of w is equal to 1 upon ts. This x of t is converted into x of omega, and these all terms will be get converted into some frequencies of addition and subtraction, and these are nothing but the continuous spectrum, and that spectrum will be added and subtracted with the parameter 1. So here we will get a final equation y of omega is equal to 1 upon ts summation n is equal to minus infinity to plus infinity x of omega minus n omega s. Here n are nothing but it may be 0, it may be plus minus 1, plus minus 2, plus minus 3, etc. So it becomes a very symmetrical wave with respect to the vertical axis. Now just concentrate that we have taken the sampling frequency is greater than twice fm. So there may be the possibility that fs can be less than twice fm, less than greater than twice fm, or it may be the equal to twice fm. So in case of fs is greater than twice fm, we get a sampled signal apart from each other. That means they are creating the hollow space in between the two frequency spectrum, and that can be called as a images or the guard band. Because of this, the all frequency spectrum as get separated from each other and they can be recovered very well in the time domain. If it is fs is equal to twice fm, then it is called as the perfect sampling. Here, if you look at these triangles, then all frequency spectrum are very much close to each other. That means as soon as the one frequency spectrum ends, immediately second frequency spectrum starts because both frequencies are equal. But if the sampling frequency is less than twice fm, then it is a case of undersampling. In case of undersampling, the two frequency spectrums are get overlapped on each other, and hence because of that overlapping the signal may get lost. Now this loss of the signal cannot be recovered back using any parameter or any technique, and this is called as the aliasing. Aliasing is a phenomenon where high frequencies took the identical to the low frequencies because of the low sampling frequency. In order to represent a continuous time signal faithfully, we need to take as many samples as possible. This is done by the analog to digital converter having a high sampling. The sampling theorem indicates that the sampling should be done always with a fs is greater than twice fm, that means oversampling, or in the worst condition it should be the perfect sampling. But if you goes with the undersampling technique, then the signal can be lost. This figure shows that how the oversampling and undersampling takes place. In above figure, the samples are taken in the more number. Here the red vertical lines indicate the number of samples, and in below figure that samples are very less in number. So if you take the more number of samples, then the original signal can be recovered in a very good shape. But if you take the samples are very less, then the original signal cannot be recovered back. Let us now see that what is the effect of aliasing. If the sampling frequency is greater than twice f max, then there is no aliasing, and that can be shown with this figure. Here the both frequency band, that means this band and this band along with this band, they are much separated from each other, and hence there is no aliasing, that means that there is no overlapping. But if you look at this figure, here this part and this part are get overlapped on each other, and because of that this portion is get overlapped on each other. This overlapping will cause the signal loss, and that frequency is called as the aliased frequency. So if the sampling frequency is kept smaller than twice f max, then it causes the aliasing, and aliasing will cause the signal loss. If aliasing occurs in the signal, then there are the chances of folding frequency as well. The Nyquist frequency, or sometimes it is called as the folding frequency of a sampling system, is nothing but the half of the sampling rate of a discrete processing system. Now look at this figure. In this figure, the portion from origin to Fs is called as a folding. Here one fold is taken place, and exactly half of this fold, that means this peak, is called as the 0.5 Fs, that means half of the Fs. So that frequency is called as the folding frequency, which is equal to Fs divided by 2. One point should be noted down here, that Nyquist rate and Nyquist frequency both are different. Nyquist rate is the property of continuous time analog signal, and Nyquist frequency is a property or parameter of the discrete time discrete system. That means Nyquist rate comes in a picture for analog domain, and Nyquist rate comes in a picture in case of digital domain. Now sometimes it may happen that in spite of our opinion, or in spite of the many efforts, that sampling frequency cannot be increased beyond the limit, because sometimes that highest frequency present in the analog signal are no higher than half of the sampling rate, and that causes the aliasing. So in such cases, what will be the solution to avoid that aliasing, or how to remove the noise that present because of aliasing? So in such cases, the use of low pass filter is preferred before the analog to digital converter. Now this filter is called as the anti-aliasing filter, because this signal try to reduce the higher frequency component, which will causes the distortion. This low pass filter will cuts off all the high frequency signal and passes only the low pass frequency signal. This high pass frequency signal, which will introduce some error or which will introduce some disturbances in the signal, can be removed with the help of that low pass filter. And such low pass filter will create the band pass signal for analog to digital converter, and that low pass signal only be converted into the sampled form, and this filter is called as the anti-aliasing filter. So it means that they have a infinite frequencies present in them. An anti-aliasing filter are basically the low pass filter which are used to remove the high frequency from the input signal, thereby making them band limited signal. So in this case, use of anti-aliasing filter will remove the chances of aliasing and hence the disturbed noise. Let us now solve one example, that how an analog signal is converted into the discrete signal. So here I have taken the two examples for the practice point of view. The first signal, consider x1t is equal to cos of 2 pi 10t. Here sampling frequency is given as fs is equal to 40 Hz, and we want to find out its discrete signal. Now this x of n can be found out using replacing this t by n by fs. Now here t is replaced by n by fs, and as fs is equal to 40 Hz, it will be become n divided by 40. So from this equation, the t, that means time domain parameter, is replaced by n upon fs. So here t will be replaced by n by 40, and we become cos of pi by 2n. Similarly, in the second equation, this this cos 2 pi 50t. So again t is replaced with n by 40, and it becomes cos 5 pi by 2 upon n. So I hope in today's lecture what I taught about sampling theorem, aliasing, and the sample conversion from analog to digital domain will be very well understood by everybody. So just go through the more PPTs what I shared, and keep in touch in case of any problem. Thank you very much.